This is content of part 5a, if you're interested only in specific part of this video. Just jump to its start time. Next I will talk about analysis of measurement of anisotropic field and what kind of data we can get from this measurement. This is measurement of anisotropic field as function of perpendicular external magnetic field. The first things to notice that anisotropic field increases near linearly with increase of perpendicular external magnetic field. It is not hard to understand the reason why. The stronger the perpendicular magnetic field is, the stronger the in-plane magnetic field is required in order to turn the magnetization from the perpendicular magnetic field, and therefore the larger the anisotropic field. The slope of this increase is determined by the strength of the spin-orbit interaction. This slide explains the reason why. When we have some inclined magnetic field in vacuum, the spin is exactly aligned along this field. In a film, the external magnetic field excites or creates the magnetic field of spin-orbit interaction, whose direction is perpendicular to the interface and whose magnitude is proportional to the in-plane component of the external magnetic field. As a result, magnetic field of spin-orbit interaction misaligns the spin, and the spin is not more aligned along the direction of the external magnetic field. In the case when coefficient of spin-orbit interaction is positive, the spin is aligned away from external magnetic field towards the film normal. In the opposite case, when coefficient of spin-orbit interaction is negative, the spin is aligned away from external magnetic field towards the in-plane direction. Let us check how this fact is described mathematically. Please go to my page on perpendicular magnetic anisotropy, PMA. Just below content, open the file calculation Anisotropy PMA PDF. Go to the page 10. This is a question for the calculation of the anisotropic field as the function of perpendicular external magnetic field is Z. As anisotropy is 0 is the anisotropic field in absence of any perpendicular external magnetic field. K(SO) is the coefficient of spin-orbit interaction. This under square root is this one is a small parameter. When it is ignored, the formula to simplify to this formula, this 6.10, which reads that the anisotropic field minus the perpendicular external magnetic field is linearly proportional to the coefficient of the spin-orbit interaction. Therefore, the slope of this increase just directly proportional to the coefficient of the spin-orbit interaction. As this formula indicates, it is not anisotropic field itself, but the difference between anisotropic field and external magnetic field is important. In fact, this difference is a parameter which describes this effect. The difference, which equal to 0, means the spin is exactly aligned along the external field. A positive difference means that the spin is tilted from external field towards the film normal, and therefore coefficient of spin-orbit interaction is larger than 0. A negative difference means the spin is tilted from the external field in the opposite direction towards the in-plane direction, and therefore coefficient of spin-orbit interaction is smaller than 0. It means that for analyzing the anisotropic field, another parameter is more important and more revealing. It is a difference between anisotropic field and the perpendicular component of the external magnetic field. These graphs shows the calculated difference for two scan directions. The data for this are taken from this graph, and data for this graph taken from this graph. As y-axis, the difference between anisotropic field and an external magnetic field is used. As x-axis, the absolute value of external field is used. As you can see, the data for the scan along and perpendicular to the current are nearly the same as it could be expected. What is important about this graph? What kind of information can we get? First of all, the slope of graph is important. In the case of this particular nanomagnet, the slope is negative, meaning that coefficient of spin-orbit interaction is negative. For example, in the case of a multilayer nanomagnet, the slope is usually positive, meaning in that case coefficient of spin-orbit interaction is positive. There is additional merit of this graph. In comparison to this graph, the oscillations are more clear in this graph. The current dependency is more clear as well. Lines of different color correspond to different current density. This particular nanomagnet is relatively thick. That is the reason why its coefficient of spin-orbit interaction is negative. Slope is negative. You can find the data of measured coefficient of spin-orbit interaction along other many measured data about all nanomagnets I have already measured in this web page. Just go here. Yeah, all measured data. And slightly down. This table is summarizing the measured data of all measured nanomagnets for each wafer. The nanomagnet, which as I just showed you, is from wafer Ha.05a. As you can see, all nanomagnets of this wafer have a negative coefficient of spin-orbit interaction. However, in case when a nanomagnet consists of many layers and therefore has many interfaces, coefficient of spin-orbit interaction is usually positive and often large. You can see for a single layer nanomagnet, coefficient of spin-orbit interaction is sometimes negative, sometimes positive, but mostly it's negative. But for multilayer nanomagnet, coefficient of spin-orbit interaction is mostly positive and often large. For wafer Ha.05a, coefficient of spin-orbit interaction is about 8. It is huge. You can check the nanomagnet structure and measure property by clicking on it. For example, this one. You can see this nanomagnet consists of 6 iron boron layers with tungsten layers between them. This structure has many interfaces. Each interface contributes to spin-orbit interaction. As a result, coefficient of spin-orbit interaction becomes large for this layer. As I explained before, the deformation of atomic orbitals at interfaces is a key to increase the strength of spin-orbit interaction. This sample has a lot of interfaces. This is the reason why spin-orbit interaction is so strong in this sample. Let us take a look at a measurement of some nanomagnet from this wafer, Ha.05a. Just go to the folder with this wafer name Ha.05a. Let us check the data of the nanomagnet name Ha.05a. So it means that the anisotropy field is measured as function of current. You can either copy paste here, copy, paste here, or to navigate to the folder from here. Next, press Read All. As you can notice, the current dependency of anisotropy field is stronger for this nanomagnet because of stronger spin-orbit interaction. But what we're looking for is the slope here. As you recall, the previous nanomagnet has a negative slope. However, in the case of this nanomagnet, the slope is positive and very large, indicating a very strong contribution of the spin-orbit interaction to the magnetic properties for this nanomagnet. I want to compare it with previous nanomagnet again. Just copy-paste the directory of that nanomagnet here and read all data. The slope is negative. Next, I will explain about evaluation of coefficient of spin-orbit interaction and anisotropy field and fitting of the oscillations. This theory predicts that anisotropy field depends linearly on the perpendicular external magnetic field as that. The experimental measurements follow this general linear dependence. However, there are substantial oscillations on the top of the linear dependence. This fact should be carefully taken into the fitting procedure. As I have told you, there are several observed types of oscillations for evaluated parameters of this measurement. During the previous fitting, we see the oscillation due to angular dependence of spin-orbit interaction. The amplitude of this oscillation is small. In contrast, the amplitude of oscillation of anisotropy field, which we see at this step, is relatively large. They are due to the dependency of spin-orbit interaction on the magnitude of the applied magnetic field. This oscillation is a very important parameter of a nanomagnet. We will fit and study them carefully. Even so, the oscillations are large and it makes some difficulties for the fitting. Still, it is possible to fit it and to extract both the parameters of linear dependence and the parameters of the oscillations. Those parameters are very important characteristics of nanomagnet for a variety of different applications. this part of program is doing the fitting. This is the same graphs as this ones, but both part of data which are measured at negative and positive magnetic field as that are shown separately. These graphs are the same as this one, but they show the data averaged over different current density. The white line is for the positive HZ, the red line is for negative HZ, the green line is the average between red and white lines. Now I would like to talk in more detail about the dependence of anisotropy field on the polarity of magnetic field, about this observed difference between white line and red line. You can notice there is a difference between anisotropy field measured at opposite polarities of external magnetic field. The difference between white and red lines. There are two kinds of this difference. The slope is different. You can see the gap is increases with the magnetic field, gap between red and white lines. Additionally, there is a difference even in the absence of magnetic field. The gap exists even in the absence of field, or more precisely, at a very small field. These are two important measured data which have different origins. The difference in slopes is due to the polarity dependence of the spin-orbit interactions. It means that the strength of spin-orbit interaction may change when the external magnetic field is reversed. As I have explained in the previous video, the strength of spin-orbit interaction depends on degree of deformation and the type of deformation of the atomic orbitals by external magnetic field. Due to the Lorentz force, the clockwise and counterclockwise paths of orbitals shifted differently with respect to the nuclear. One part is shifted closely to nuclear, and another part is shifted more far away from nuclear. It creates magnetic field of spin-orbit interaction. The strength of magnetic field of spin-orbit interaction depends on deformation of orbital, but also it may depend on polarity of external magnetic field. For example, in simple case of elliptical orbital, only this part of orbital, which is close to nuclear, mostly contribute to spin-orbit interaction. This orbital part may move either more closer or move far away, depending on the polarity of the external magnetic field. That is the reason why the spin-orbit interaction may depend on the polarity of the magnetic field. The difference in slopes between red and white lines is due to the dependence of spin-orbit interaction on the polarity of the external magnetic field. But the zero field, here and here, but the zero field difference is due to the dependence of spin-orbit interaction on the polarity of the magnetization. The magnetization is reversed at rather weak magnetic field and creates these steps. The magnetization creates a magnetic field itself, due to which there is a polarity dependence of spin-orbit interaction. However, some samples show a relatively large zero field difference, and it might require another contribution for the explanation. One possible mechanism which may contribute to this difference at zero field is the Geolocian-Maury exchange interaction. You can read it maybe in here in Wikipedia. Both difference for reversal of external magnetic field and reversal of magnetization depend on geometrical symmetry of the nanomagnet. The dependence on anisotropic field on the polarity is very different for geometrically symmetrical and geometrically non-symmetrical nanomagnets. In the case of the symmetrical nanomagnet, there are two symmetrical but opposite interfaces at each side of nanomagnet, like iron-boron tantalum and tantalum-iron-boron. The difference of spin-orbit interaction for opposite direction of external magnetic field is equal and opposite. In total, there is no dependence of spin-orbit interaction on the polarity of external magnetic field. For example, for this direction of magnetic field, the magnetic field goes through the interface from tantalum to iron-boron in the case of low interface, and in opposite direction from iron-boron to tantalum in the case of upper interface. When the magnetic field is reversed, nothing changes. The magnetic field still goes once from tantalum to iron-boron and once from iron-boron to tantalum. However, in case of non-symmetric nanomagnet, having two different interfaces, there is no such compensation, and spin-orbit interactions is different for opposite polarities of external magnetic field. The nanomagnet measured here has two very different interfaces. The first interface is tantalum iron boron, and the second interface is iron M0. As you can see, slopes are clearly different for opposite direction of external magnetic field. Next, let's take a look at measurement data for more symmetrical waveguide. For example, Ha.05a, which has many identical interfaces. It has still asymmetry between top and bottom size, but these two interfaces are only two asymmetrical interfaces among many symmetrical interfaces, so can be neglected. So let's copy paste directory here and read. The difference is small as we expected. Next I will show you how to do fitting. In order to proceed, we remove this polarity dependent effect by averaging data of opposite external magnetic field. The green line is the averaging of white and red lines, which is used for the fitting. This is the fitting parameters. For the fitting, press Analyze as Anisotropy. As you see, the fitting is not so bad for both the linear increase and the oscillations. The fit is nearly the same for both scans. After fit, these graphs shows only oscillation spots, and it's good. This is obtained parameters from the fit: anisotropic field in kilogauss, coefficient of spin-orbit interaction, steps for the magnetic field reversal, and parameters of oscillations. I will refer anisotropic field as anisotropic field in absence of any external magnetic field here. Next, let's do the fitting for previous nanomagnets. So copy its directory here, read, press Analyze anisotropic field, and you can see fit is not so good because of some problems for small magnetic field. At small magnetic field, some magnetic domain may exist for some nanomagnets. So for this purpose we just limit the fitting for higher magnetic field for this one. So let's reload data again and fit again. Now it's very good. If you are interested to see the content and other parts of this video, you can find the links below this video.